Nippy outside this morning. Everybody signed it? You did sign it. We'll put it back here, and Tom will be the keeper of it if anybody else comes in. Did you sign it? Yeah. You sign it and then over here. Well, good morning. I think we're all ready to go. Is that right? Like ready to go home, probably, in the cold. But I guess we'll be ready to go with Pre-Cal instead, Trig. We do have a test coming up there on Thursday. So on Thursday, we'll be coming in, having our test over those first 4 sections of Chapter 8, and also that little first part of Chapter 14 that we've been looking at. I gave you some problems on the study guide that were similar to the ones we'll have from Chapter 14, okay? We're going to look at those a little bit more today as well and look back. Trying to remember, we got a little bit into that Chapter 14 material on Thursday, so we'll see how we're doing with that. And maybe you all started on the study guide. Hopefully you did get my email, right, about what was posted on D2L. Let me go over here to D2L just a moment. I think where I wanted to be was actually at the course home. I wanted to just point out to you over here on D2L that I've posted some information here about your final exam. The retake test day, remember, will be Tuesday, December 2nd, where you can take a test of your choice. Now, I plan to get that third test back to you next week before Thanksgiving break. Next week we only have, well, you all go to school Monday and Tuesday, here just Tuesday. So I'll have to have that back to you by next Tuesday so you can make a decision about what test you're taking, okay, on the retake day. Test 3 is what's coming up right now, so I've got a little bit of information here about that, and I'll provide a blank unit circle. I don't really know that we need a blank unit circle, but I'll put one on there anyway just in case anybody's wanting one. But I'll give you the formulas for the law of sines, law of cosines, and the area of the triangles, okay? And I've told you here where the study guide is located for this test. So hopefully that'll be useful there as we go through. Any questions about what's going on or dates coming up? It's all coming fast is what's happening, okay? Things are moving really quickly for us now. So, but our first deal right now, you know, we like the day-by-day thing, or at least that's how I try to live anyway, day by day, because I can't plan for anything. But right now, our only plan we have right now is to be ready for this test on Thursday. Okay, that's what we want to focus on at this point. All right, so everybody knows where we are then and what's going on, correct? Very good then. Let's go then back to where you were looking at last time. We had talked about the area of the triangles, 2 different formulas we looked at. One for use if we had a side angle side given to us, but you know we didn't know the height of the triangle, so we could work with 1/2 AB sine of angle C, or 1/2 times 2 sides times the sine of the angle that's included between those 2 sides. That's what that formula was. The other one was Heron's formula, and it was useful if we knew side, side, side. If we knew all 3 sides, we could use Heron's formula. So in order to use Heron's formula, though, first we did have to find that value of S, which was just half of the sum of the sides measurements. So let's look back just a moment in section 8.4 over on page 538, if anybody had a question back there. In 8.4, we were looking at the area of the triangles. We had 2 formulas. One was K equals 1/2 AB sine angle C. The other one was K equals the square root of S times S minus A times S minus B times S minus C, where S was equal to half of A plus B plus C. The second one's called Heron's formula. First one doesn't really have a distinct name like that, but okay. We use the second one with side, side, side. The first one if we know side, angle, side. Okay. Anybody have a question back there on that part? Probably those problems, I'm guessing, were a little more straightforward than some of the things we've been working with. These formulas, I guess, are a little more straightforward, aren't they? You all found that they were? That reminds me, though, you will want to bring a calculator on Thursday, one that you know how to operate, and one that's not on a cell phone, okay? So bring a real calculator Thursday, because working with these formulas, we are tending to use them some in this part on solving triangles and finding areas, and I'll tell you what place I want you to round to, okay?
We're going to be given all the formulas, right?
Back on the other screen where I was looking, I said I'll give you the law of sines, the law of cosines, and the area formulas, okay? So what I'm not giving you are things like still those basic identities that I feel like we've worked with since the beginning. I don't think I even gave those to you in the beginning, right? So like the tangent of an angle is equal to the sine of the angle over the cosine of the angle. Those types of identities, I'm not giving those to you. I mean, I expect you to know those. I'm not giving you sine squared theta plus cosine squared theta equals 1 or any other of the Pythagorean identities. I expect you know those. I'm not giving you things like the sine of an angle equals the opposite over the hypotenuse. Again, I expect you to know those things. I will give you the law of sines, law of cosines, and the area formulas. Okay. And like I say, I'll have a blank unit circle on there. You might use it for some things, but overall it's not as useful, I guess, in this part that we're doing right now. We haven't referred to that as much in this last little bit. All right, well, let's go on back up to the limit part then, over on section 14:1 and 2. And I think I had only asked you to maybe look at a little bit from section 14:1. Is that correct, on using a table to find the limit? That's what I wrote down. I don't know. I might not have written it all down. So let's go back over there, though, to page 870 a moment. I want to talk just a little bit more about limits today and how to look at a graph and figure out what the limit would be. Remember, we kind of had to take a deep breath to go from what we'd been talking about over to the part on limits there. So let's go back into limits a minute. So chapter 14. First off, just to kind of repeat a little bit of what we said last class, the limit as x approaches some value c, the limit of some function f of x, then as x is approaching some value c, we said would be equal to some number n. Okay. We said the limit is talking about the behavior of the function. In other words, what's happening with the function as x approaches c? So what value is the function f of x approaching as x approaches that value c? Okay, we're saying it's whatever that value is, that's what we're calling n out there. Okay, that's what it's approaching, what the value the function's approaching. We're looking at what's going on with the function when the x's are getting closer and closer to a particular value. And we look at what happens as the x's approach that value from both the left and the right. Okay, and that's why last class we drew a table up here, an xy chart. Do you remember that? We had some function, I don't remember what it was, maybe 3x squared or y equals 3x squared, something like that. We drew a xy chart. We plugged in values for x that were getting close to whatever the c value was, but we plugged in values from both directions for that, okay, to see what value the function was approaching from either direction. All right, so that's what they want you to do over on page 870, was to make tables to find the limits. We also noticed last class that sometimes we can just plug in the value and get the answer, right? Sometimes we can do that. We talked a little bit, I believe, last time about how we can do that if the function or if the graph is continuous. If we don't have to lift our pencil when we draw the graph, then we should be able to just plug the value in and get the limit value. Normally that's what you try first when you have a limit problem. Just try plugging the value in. There are some cases where it will not work because maybe it's a fraction and it gives you something undefined. It gives you a 0 in the denominator of the fraction. Those don't work, so we have other methods for those. Unfortunately, in this class, we don't get into too much detail with that, but come see me for calculus next semester. We'll talk about that some more. Okay? All right, that's my advertisement for calculus. I'll have to work on it better than that, won't I, to recruit you all. All right, over on page 870, let's look over there just a moment. Like on number 9, they want you to do a table, but we said last time, you know, if we can plug the value in and get something out, then that's what we would do, just algebraically, just evaluate it. So this is the same as then the limit as x approaches 0, and put 0 in for the x. Does that work out? 1 over 1. The limit as x approaches 0 of 1 will just be 1. It's always true that the limit of a constant is the constant value itself. So once we can get that part, that function to that constant value, that's going to be our answer there. So in this case, we could have done a table. Did anybody do a table for this one? You plugged in values? Okay, and did it appear to approach 1 as you did that? So that's what they intended for you to do, is, you know, put up a chart up here, plug in values as x approaches 0. So maybe like, maybe you started with -1, -0.5, -0.1, -0.01. I don't know. There's 4 values we could have plugged in. Did you put in any of those by any chance? Okay. -1 just gave us 0 though, right? And you didn't plug in those others, so let's see what we've got here. F of -5. Just to kind of see, I'm sorry, -0.5. So that would give us 0.5 over, that's going to be a 0.25 plus 1, so 1.25. So what's that going to give us? One half times 2/5, 0.4. Yeah. Okay. 0.4 there. I just had to think through it. I'm sorry. So I had to think through it a minute. So, because it was 1/2 divided by 5/4 is what I was thinking. So that's 1/2 times 4/5. It's 2/5 or 0.4. That's a decimal. That's not a negative. It kind of looks like a negative. Let's change that. And then if we put in the -0.1, what do you get when you put in -0.1? I'll let somebody figure that one up for us, just to see that this value is getting close to 1 here as we come in towards 0 from the left. Looks like we come down to 0.9 over 1.01. So what's that? Did you get it there? -0.1 when you plug that in? 0.9 what? 0.91. Okay. And so already we can tell we're getting closer to that 1, but what if you put in that -0.01? Plug that last part in for me. We're plugging that value, by the way, into this function up here. Everywhere there's an x, we're putting in that value. That's what we're doing. That's the function we're working with, remember? So what do you get when you plug in -0.01? What'd you get? You have it back there? 0.99. Somehow that's what I thought we were going to get there. So it's approaching 1. But we also said we want to look from the other direction as x is coming closer to 0 from the right side of 0. So what values might we use there? What was something you already used? Okay, you used 1, and then what else closer into 0? Okay, that was it. Okay. Well, I'm going to use 0.1. Okay, how about that? So we'll use, when I plug in 1, that's just going to give me, 1, right? 1 plus 1's 2. 2 over 2, it looks like I get 1 when I put in 1. What about when I put in 0.1? What do you get for that one, plugging it in? It's good practice there just to see what you're getting there. What do you get when you put in that 0.1? 1.09? Okay, we were working with x as approaching 0. This one's interesting because at 1 it is equal to 1 there. So that's kind of interesting there. But it's approaching 1 there. What if you put in 0.01? What do you get for that one? I'm just curious now. What do you get for 0.0? 1.009. Thank you. Okay, so we're approaching 1. Well, obviously here, I guess it's obvious, probably the easiest thing for us to do was to just plug 1 into the function. I mean, not 1, but 0 into the function, because remember, it was the limit as x approaches 0. So if we can plug that number in and get a value out, that's what we would prefer to do rather than doing this table. Tables are kind of tedious. They help us see what's going on, but if we can plug that value in and get something out of it, then that's going to be our answer. Okay, that's going to be what we work with there. So that's one type we're looking at. We have some like that on the study guide, by the way. So let me pull one of those up here while we're kind of in the middle of talking about this. So this is, I'm going to go down to 29. 28's like this too, but this is from the study guide.
Number 11.
Yeah, just a second. Okay, limit as x approaches 2 of x squared plus 4x plus 1. Okay. So can you just plug this value in? Yeah, you should be able to. What kind of graph is f of x equals x squared plus 4x plus 1? What kind of function is that? It's a parabola, right? It's going to be a quadratic function, so it's a parabola. It's a continuous function. That's a continuous graph. So we've got 2 squared plus 4 times 2 plus 1. And that's going to be 4 plus 8 plus 1. And now we're at the part where we get the numerical value 13. And the limit of a numerical value, a constant, we call that the limit of a constant, is just the constant. Okay? So that's without plugging into a table. This was off the study guide, and you can just plug the value in there, okay? And see what you get out. 28 works the same way on the study guide. Okay, there was a question about number 11 from the textbook, so let's go over to number 11 here on page 870. We had the limit as x approaches 4 of x squared minus 4x over x minus 4. And did you use a table? You just wanted to plug it in, but you couldn't. Because when you put 4 in, what happens? Yeah, we get 0 in the denominator, so that's no good. But here's how we get around that, okay, algebraically. Now, obviously, you could use a table. You could use a graphing calculator and put this in and see what the graph looks like. But to get around that algebraically, one of our techniques we use is factoring. So up in the numerator, I can factor out an x times x minus 4 over x minus 4, and that takes away that part that's messing us up. Okay? so that now I'm just working with the limit as x approaches 4 of x. So that's going to be the limit as x approaches 4 of 4 is going to go in place of the x, and I just get 4. Okay, so if we were to look at this on a table, anybody do a table for this one? Did you do a table? Did it approach 4 for you?
Yeah, 3.99 it actually gave me 4.
Okay, so when you plugged in 3.99, it actually gave you a 4. All right, so we can see it from a table. If you use that table, you would see that it is approaching, but algebraically, here's what we do if we're not using a table. Here's one technique to get around that. There are some other ways to get around that, but we won't, again, that won't come into this semester right now. But here's one of our best methods probably to get around those undefined values is to try to factor and cancel. If you can factor and cancel, then you can usually figure out what it would be. Okay. So that's a good one to look at to kind of bring that out. Now they also gave us some graphs in here for us to get the limit from the graphs. And I had you all look, I think, just at the first graph there maybe. And I'll try to put it up here. Let's see, the limit as x approaches 2 of some function, whatever it is we've got graphed here. It looks like this. Whoops, can't stay with the point there. We'll try. Well, that doesn't actually loop. It just goes up into a point, okay? Like that. All right, so let's try to fix it up a little bit better. The question is, as the x's approach 2, what are the y's approaching? What are they approaching? 3. And you can see that from the drawing, right? Barely on my drawing. But as the x's are getting closer to 2 down here, coming in from the left or the right, coming from the left, we're looking at this piece of the function coming in from the left side of the 2 on x. And we see it's getting closer and closer up to this point here, okay, the point in question. And coming from the right, we see also you know, here we're there, when we're at 2.25 maybe, we're there, 2.1. The idea is that as the x's are getting closer to 2, those y's are getting closer to 3. They're converging in on that point at 2, 3. They're both going to that point, 2, 3. So we say that the limit value is the y value. The limit value is the y value. It's what the value of the function is as the x's are getting closer to 2. Now, what happens here is when you have a continuous function or where you don't have to lift your pencil, then your function value would be the same as your limit value. They're going to be the same. In other words, f of 2 here is equal to 3. The function evaluated at 2 is 3 because that's where the point is at 2, 3. But also the limit as x approaches 2 is 3. Okay, because we didn't lift our pencil when we drew. Okay, that's that kind of generalized definition of continuous. But let's look at another one here. Okay, I didn't have you go down to 19, but let's go over to 19 for a moment now. On 19, again, we have the limit of some function as, this time it's as x approaches 2. And here's our drawing this time. That's the point 2, 2 right there. Okay. And actually this circle is an open circle here. Okay. The question is, what's the limit of this function as the x's are approaching 2? And first off, it is a function. Okay, remember functions must pass that vertical line test. The vertical line cannot, any vertical line can't go through the graph more than once. So that's why in that particular spot there we have the open circle, but then the closed circle, the function value is down below there. We can't have them both closed in and it still be a function. Okay, this would be like a piecewise defined function. Maybe you remember piecewise defined functions. In this textbook, they're back in chapter 2, so it's not something we covered in this particular semester, but it's something earlier on that you would have looked at. Okay, so a piecewise defined function tells us the graph's going to look a certain way between certain values, but then, like in this case, then when x is 2, the function value is going to be 2. It's telling us. So we take a break in the overall graph and how it looks up there. Because we had to raise the pencil up when we were drawing this, this one is discontinuous. Okay, yeah, I know y'all can draw the open circle and go on, but we're saying there's a gap there, that open circle. Okay, so it's a discontinuous function. What happens then is as we are approaching 2 from the left, what are our y's approaching on this graph? What are our y's getting close to? 4. They are getting close to 4. As we approach 2 on the x-axis, as our x's get closer to 2 from the right, what are our y's approaching? They're approaching that open circle point up there, which is not a real point there, but it is approaching that value. Because if I'm at this value right here where I'm marking on the graph, okay, if you look at my graph there, okay, see where I just marked a value? I come up, my y value is here. I come here, my y value is here. The y's are getting closer to 4. Okay, that makes my limit value equal to 4. However, f of 2, the function evaluated when x is equal to 2, is equal to 2, because that's where the actual point is at 2, 2. The function value at 2 is 2, but the limit value as x is approaching 2 will be up there at 4. Remember, it tells about the behavior of the function, and that graph from both directions is approaching where y's are equal to 4. Does that make sense there on that one, how they're approaching that? We're going to look at another one. I think it'll help you see it a little bit better. Let's go down to 22. Same page there. This time it's the limit as x approaches 4 of f of x. So we have a 4, we have a 8. That's how they have it labeled. 2, 4, 6, 8. Okay. And something like that. They're both open circles there this time. We want to know the limit as x approaches 4. The limit as x approaches 4. So let's look at this just a minute. As I'm approaching 4 from the left, what are my y's getting close to?
4.
They're getting close to 4. As I'm approaching from the left, I'm coming in on this graph here, right? So my y's are getting close to 4. Does that make sense how we're coming in there? So I'm at these values, so they would be up here on that graph, on that particular piece of the graph. So let me write about this over here. The limit as x approaches 4, here's a little new notation, from the left. That's what that meant that I just wrote up there. See that little negative up to the right of the 4? That means from the left. Okay? That doesn't mean anything's negative here. So as x approaches 4 from the left, you just told me the limit there would be 4. Okay? What about the limit as x approaches 4 from the right? Okay. This is like math shorthand. What's that? It's 2. That's right. Because as we come in from the right, you know, the closer we get to 4 from the right, we're up here on this kind of linear piece. I think it's a line, and mine looks more linear anyway. But we're on this piece that's coming in from the right. And so as we get closer to 4 there, our y's are getting close to 2. Okay, they're getting closer and closer to 2. So we get a 4 there, a 2 here. Well, that brings up another problem. Everything we've looked at so far, they kind of converged in at the same point. So how can we answer the question up top, the limit as x approaches 4 of this function? We're approaching different values from both sides. That tells us that this does not exist. The actual limit up there does not exist. Now, from both sides, we can say, you know, what the limit is coming in from the left, coming in from the right. Those are called one-sided limits. But the overall limit does not exist.
How do we figure that out?
The values are different from the left and the right. Okay? So I'm going to write up something here for you. Okay? If the limit as x approaches c from the left is equal to m, and the limit as x approaches c from the right is equal to n, then the limit as x approaches c does not exist. If the limit as x approaches c from the left equals n, and the limit as x approaches c from the right equals n, then, and this is the case we had seen up to this point, then the limit as x approaches c for that function will equal n. In other words, as you're coming from the left and the right, they have to converge upon a point in order for the overall limit to exist. Otherwise, you can have one-sided limits, but the overall limit will not exist. Okay? Does not exist. A lot of times they'll just write D and E for that. The values have to be the same from both directions. That's why we were even checking earlier on the table, coming in from both directions. We were checking to see, you know, what the value would have to be there. I know this is stated a little bit more theorem-like, theoretical-like. Sometimes people don't like that in math, but basically what we're saying here, you know, is that whether you're approaching the value itself on the x-axis from the left or the right, you need the behavior of the function to be the same from both directions in order for the limit to exist. Okay. Let's look at the one from the study guide for that. Okay. Let me see if I can find it back over here. I had it pulled up earlier, but there we go. All right, so on this one here, there's the question. The limit as x approaches 3 for this function. So let's write up here a minute. The limit as x approaches 3 from the left of that function will be what?
The left
From the left.
will be 3.
Will be 3. That's right. The limit as x approaches 3 from the right will be 5. Are we seeing that? Is everybody seeing that? As we're coming in toward 3, remember, as when we say as x approaches 3, we're looking down here as the x's get close to 3, but what we're having to do is look up there and see what values our y's are going to be as we get closer to 3 from the left, or as we get closer to 3 over here from the right. So coming in from the left, we're on that piece of the graph to the left. Coming in from the right, we're on the piece that is approaching from the right. Again, it's a piecewise defined function here. And so that means that for this particular problem, the limit as x approaches 3 does not exist because the values coming from the left and coming from the right are different. That's the reasoning there. Questions on that one? All right, what about the one before it, number 26? Are we ready to go back to 26? Everybody okay to leave this page? Okay. Right here. The limit as x approaches 1, as the x's get close to 1 from both sides, what are the y's getting close to? 3. Y'all like these questions. Some of you like these anyway, right? Okay. So the y's are approaching 3, so that's your answer there. Because they're both going to the same value, we could break this one up also. The limit as x approaches 1 from the left. Well, as we're getting close to 1 from the left, we're on this piece of the graph. Our y's are getting close to 3. The limit as x approaches 1 from the right. Then we'd be approaching from this side here. Likewise, they're approaching 3. So therefore, the overall limit is 3. Okay. Questions there? There's some others over on page 877. You can just plug the values in to algebraically evaluate if you want to, test yourself on that. We already said that the limit of a constant is a constant. Whoops, I kind of got that off, didn't I? So, for example, if I go, let me go back over here a moment. This is number 8. There it says the limit as x approaches 1 of -3. Okay, so that tells me this value should be -3. Okay, the limit of just a numerical value, no variable. It's just going to be that numerical value. So what's happening there? Why is that? Remember this part here represented f of x. Remember that on our initial write-up? So this is telling us that f of x here is equal to -3. It's another way of saying y equals -3. What does the graph of y equals -3 look like? All right, must be too cold to answer today. Okay, y equals -3 is going to be this horizontal line here. So the question that we started with, the limit question, says, as the x's are approaching 1, there's 1, as the x's are approaching 1 from the left and the right, remember we know now that the values coming in from the left and the right, they have to be the same in order for that limit to exist. But as the x's are approaching 1 from the left or the right, what's happening with my y values here on this graph? They're staying at -3, right? They're staying at -3. So that's why we say the limit of the constant, or the limit of any constant, is just going to be that constant value because it's not changing. The y's aren't changing here. So we don't draw that out every time, but I want to illustrate for you what's happening just when we say the limit of a constant is that constant. Okay. And then the another one over on this page that you might plug into, I used this one in yesterday's class, and they wanted to use a calculator. You don't need a calculator for this. x is approaching -1. Here's the function. We always try, we said just plug in the value first, see if it works. This should work out because this is a polynomial function. I don't know if you all remember studying polynomial functions maybe somewhere in a past class. Again, that's in the first part of this textbook that's not included in this semester. But polynomial functions, generally, you know, they curve in some way. There's lots of little curves in between. They have specific start and ending behaviors. They are continuous, though. So what happens here? When you plug in -1, forgot to still write my limit part here. I haven't done the limit yet, so I should still write that I'm taking the limit. Even though we know it's going to be whatever it is that we get here. Well, you're just raising -1 to power, so it's either going to come out being +1 or -1 on those pieces. -1 to an odd power is going to be what? Still be negative. Still be negative. Here it's to an even power. We got -8 plus 7 plus 8 minus 1 minus 4. So what'd you get? 2. Isn't that a 2? Looks like 2. Okay. So again, we got it just by plugging in the value to see what we got there. So for a little extra practice, you could work with some of those over on page 877, just plugging in those values there. Any questions on 20? Okay. What about this one here? You may know what that graph looks like. What does that graph look like? It's what? What do you mean across the x-axis? Okay, it actually does not cross over the x-axis. It's a reciprocal function. It's considered one of our more basic functions. It graphs like this. This is my sketch of a graph, okay? It may not be precisely right, but does that bring back a memory for some of you from a previous graphing? 1 over x. It's one of our common functions. There's a particular group of functions that we kind of reference a lot. One of them's the square root of x. We should know how these graphs look overall. Okay, y equals square root of x, y equals 1 over x, y equals the absolute value of x, a basic linear function, horizontal and vertical lines. Those are kind of in our library of functions there. So this one I'm showing you what the graph looks like. You could plug in your values if you wanted to and verify here. But what if I wanted to know this? The limit as x approaches 0 for this function. Obviously, I cannot just put 0 in for x here. What else do I notice about when x is equal to 0? What do I notice here in this function when x is equal to 0? What about the function itself? Yeah, right, it's undefined there, okay? The function is undefined when x is equal to 0. Now, what's happening here is we have asymptotes. You remember studying asymptotes with rational functions? We have a vertical asymptote coming down through here on the y-axis where x is equal to 0 because we just said this function is undefined when x is equal to 0, so that tells us that line is our vertical asymptote, meaning these pieces of the graph are not going to cross over it, okay, because we don't have a value there. It's also true we have a horizontal asymptote at y equals 0 here on the x-axis. Reason being, this function will never be equal to 0. It can't equal 0 because in order for a fraction to equal 0, you must be able to get 0 up in the numerator. This numerator is strictly 1. There's no variable up there that we can plug in for and make it equal 0. So this graph it's getting closer and closer to the x-axis as well as closer and closer to the y-axis, but it's not going to cross over either one, okay? So just to kind of look at the graph itself. Now, what about as x approaches 0? Let's go back to our one-sided limits here. Limit as x approaches 0 from the left of this function, and the limit as x approaches 0 from the right. What are they? What would you say the limit is as x approaches 0 from the left? Step over here just a moment. As x approaches 0 from the left, what's happening with our graph? Where are our y's going?
Down, 0.
They're going down, and they're keeping on going down, right? Negative infinity is what we're looking for there. They keep going down. The y's are getting lower and lower, okay? They're going to negative infinity. We don't really know where they go, but they're going where we can't count them, okay? Negative infinity. Because as we get closer into 0, that graph keeps going down. What about as we approach 0 from the right? Those are going up, so those are going to infinity. If from one side it's approaching negative infinity and from the other infinity, what do we say about our overall problem up here? The limit itself, yeah, still doesn't exist because those are two different values. Okay, they're going in different directions. We're not converging into a single point. Okay, so this is just kind of an interesting case to look at, so I thought we'd put it up here. Again, for some more algebraic practice here, you might practice with the problems over on page 877. You could practice with any of those just for some more algebraic substitutions. Okay. Any questions there about limits? That's all we're doing with limits at this point. Okay. So what about questions about everything else we've done? Okay, so what have we done? Let's think a minute to kind of get ready for this test. We know the test is coming up on Thursday. We've done 8.1 to 8.4. We've done a little bit in pieces of 14.1 to 14.3. Okay, we've done pieces of that. But you've got problems I put on the study guide that would be more similar to what you would look for from that part. Okay. We started out talking about triangles. We did a lot with triangles. That's all Chapter 8's about. It's triangles and solving triangles. So we worked on solving triangles, which means finding all missing angles and sides. Okay. In solving triangles, we first worked with right triangles. In working with right triangles, we looked at the sine was the opposite side over the hypotenuse. We did right triangle trigonometry. Cosine was the adjacent side over the hypotenuse. And the tangent was the opposite side over the adjacent. That's our right triangle trigonometry right there. Some of you referred to it as SOHCAHTOA, and we also talked about it could be stated as some old hippie caught another hippie tripping on acid. So there were some ways to try to help you remember, because I know a lot of times it's hard to remember. Well, I've been told that it's hard to remember. Now, how did we go with that SOHCAHTOA? Where's that? What are my letters there? You know, I don't know. But you can definitely remember some old hippie caught another hippie tripping on acid, I think. But now, from previous chapters, we also wanted to remember that then the cotangent, the secant, and the cosecant are all reciprocals of these, just like before. That part does not change. So we don't really have to have a new sentence to talk about those. So we just know here, let's see where we're going to go. The cotangent is the reciprocal of the tangent, just like it always has been. The secant is the reciprocal of the cosine. Again, we've done that before. And the cosecant is the reciprocal of the sine. Okay, so those are what we knew back about right triangle trigonometry. Through the use of the right triangle trigonometry, as well as through the use of the Pythagorean theorem, those allowed us to be able to solve right triangles or find missing sides and angles. Okay. Then we got to the part where they were not right triangles. What kind of triangles are they if they're not right? Wrong. If they're not right, they're wrong. No, they're oblique. You're right. Okay? All right. So we got to the oblique triangles. With the oblique triangles, we looked at two different methods to solve those. One was the law of sines, and one was the law of cosines. These were sections 8.2 and 8.3. Law of sines was 8.2. Law of cosines in section 8.3. It all depended on what we knew about the triangle, right? To use the law of sines, we said we had to know a side and the angle across from it in order to be able to work with those. And if we knew those, then we could set up the proportions. The sine of angle A over side A is equal to the sine of angle B over side B, which is also equal to the sine of angle C over side C. So we could set whichever two equal to each other that we had the information handy to work with. So I'll put up here must know an angle and the side opposite that angle. You'll have to have one other piece of information too, either another angle or another side, but we have to have this thing going on for us at least in order to set this up. The other thing about law of sines was we had what we called the ambiguous case. What was the ambiguous case? Yeah, angle side side, the ask case, right? So when we knew angle side side, basically we're just knowing one angle here, and it leaves too much leeway with the other two, and so it could result in 0, 1, or 2 triangles. Okay. And we had to determine which that would be. 0 triangles was the easiest because it would come up as an error on our calculator, or we would notice the sides were not going to be in proportion to the angles, whereas, you know, we know that the longest side has to be across from the largest angle and that sort of thing. 1 or 2 is a little more difficult, so we probably need to look at one of those here in a minute. So we'll do that. What about law of cosines? What did we, well, basically we used those. We used the law of cosines when we didn't have an angle on the side across from it, right? That was the side angle side and the side 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 situations. Law of cosines could be just stated as c squared equals a squared plus b squared minus 2ab cosine of angle C. That was our basic law of cosines. We were able to change out our variables depending on what we were given. We were also able to solve for the angle C there. Okay, remember when we solved for the angle C? When we solved for C, what did we get? Anybody remember that? Well, inverse cosine, right? Of what? You remember it?
A squared plus B squared minus C squared.
Over what?
Over 2 times A and B.
Okay. So was it a squared plus b squared minus c squared? Now I'm having a mind block here.
Yeah, it was.
Yeah. So that's right. It's a squared plus b squared minus the one that corresponds with the angle you're looking at, looking for, over the 2ab. Okay, but you can solve. I usually don't memorize that one, obviously, but I remember this one here, and you can solve for angle C in it always. You've got that one down. Okay, so that was our law of sines and law of cosines. We want to look at an ambiguous case here. I'll give you those, the formulas. I actually don't have the ones for the angle, I don't think, on my formula sheet. I have the basic one that I asterisked here. Then we had area, which we already put up our area formulas today. I'll list them back here where we're kind of generalizing. K equals 1/2 AB sine C. K equals the square root of S times S minus A, S minus B, S minus C. S equals 1/2 A plus B plus C. Okay, so we had two different formulas here. First one was used for the side angle side. Last one was used for side, side, side. Okay. And then we had our limits, okay, which we've looked at in more detail today. So we've already kind of looked at that part, I'm thinking, right? Any other questions left over on that part, the limit part? Let's look at a law of sines problem where we have to figure out if it's 0, 1, or 2 triangles, maybe for starters here. Y'all had a chance to look at the study guide there yet? A little bit? Well, does anybody have a law of sines one there that you can give us for now? I think 14, 15, and 16 we had to decide, right? So let's go over to 14 a minute. We have side A is 7, side B is 9, angle B is 49 degrees. I like to draw a little diagram, even though they're not scaled to size here. B's 49 degrees. Side B is 9, side A is 7, there's side C. Okay. We see we do know an angle and the side across from it, so we can use the law of sines. We also notice it's angle, side, side. So let's set it up here. We're going to have to say the sine of which angle? Well, 49 degrees is the only one we know, over side B, which is 9. Now, what angle and side am I going to work with to be finding here? A, it has to be A. I don't have a choice. A is 7. Side A is 7. Okay, so we're going to be looking for angle A here. Remember on these we cross multiply. So when we cross multiply, we're going to have 9 times the sine of angle A equals 7 times the sine of 49 degrees. So the sine of A equals 7 sine 49 degrees over 9. And angle A is going to be the inverse sine of 7 sine 49 degrees over 9. And that's approximately equal to, what's it approximately? 35.94 degrees. See if that's what you get. That's what the paper says. Okay, I cheated. See if that's what you get there. Remember, you want to be very careful about punching these things into your calculator with all these formulas, not just this one. You also want to make sure that your calculator is set in the correct mode, and it's in degrees. That's what we needed in for this part here. So what do we get? get 35.94 degrees. We agree? Okay, I just want to make sure we're in agreement here, okay? All right, so we know that we've got at least one triangle. The question was, do we have 0, 1, or 2? Well, we definitely have at least one because we got 35.94 degrees. So to go ahead and determine if you're going to have a second triangle, what we did to determine that was take 180 degrees, subtract 35.94 degrees. In other words, we're finding the supplement of that angle. If I take 180 degrees and subtract 35.94 degrees, what am I getting there? 144.06. Okay, so we still have that angle that was given to us. Angle B, is that what you're saying looking at the correspondence, right? Because angle B is 49 degrees and we see side B is 9. So side A is 7. Angle A must be smaller than angle B. So that cannot work, right? When we get this 144.06, it's going to be too large. We can already see from our initial drawing, which those are the three things that we were given, those two sides and that angle, they have to still be in effect there. So angle A has to be smaller than angle B, so that's not going to work. You are correct. Another way we can see is that since angle B already has to be, it was given to us as being 49 degrees, how could angle A, because that's what we're testing to see, could angle A be this supplement down here? Can this thing down here? Yeah, that adds up to more than 180, and where's the third angle? That would only be two angles adding up to more than 180. It's not going to form a triangle that way. So down here we say, no, that's not going to work. So it looks like on this one it's just going to be just the one triangle. Only one triangle. So we'll finish solving the one triangle. We'll put up that's 35.94 degrees. That allows us to find angle C by, what else do we need in there to get that to 180? Okay, so 95.06. We're doing 180 minus that 35.94 plus 49. Okay, that's where that came from. And that only leaves us side C to find. So we'll go back and set up the law of sines once again to find side C. I'm going to have to be able to see what I got up here though. The sine of 49 degrees over 9 we had equals the sine of angle C we just found to be 95.06 degrees. So we're going to have C sine 49 degrees equals 9 sine 95.06 degrees. And remember, we talked about not actually doing these calculations for the sine of each of these angles until we get to the end, because that way we will reduce our round off error a little bit. So C is equal to 9 sine 95.06 degrees over the sine of 49 degrees. So what does that equal? Side C is what? 11.88. Thank you. So does that go in proportion up here? That one had to be the longest side because it was across from the largest angle. Okay. It looks like it's all in accordance up there. Let me pull that back down in case some of you are still looking at that part down low. Now, whenever we got the supplement of what we found for angle A, and we said, well, 144.06, that's going to make everything too big because it's got to add up with that angle B that was already up there. When we found that supplement, if it had added with what we already had for angle B, and we weren't quite at 180 degrees yet when that happened, then that's when we would say, well, angle A could equal whatever this other value is we found, and we would solve both triangles. Okay, takes a little bit longer, but you would solve both at that point. Any questions there on that part? What about setting up one of these word problems here from the study guide? Did anybody try? Anybody have a question? Just in general, do you all have a question about something you've seen on the study guide? Go ahead.
I have trouble setting it up.
The word problems, I have trouble setting them up. Well, let's try one here. Do you remember one in particular that was difficult? Okay. Let's go over to 9. Okay, so I got to read it first. Okay, so let's read it, and then meanwhile be thinking about how we're going to draw this thing. A radio transmission tower is 220 feet tall. Wait, I'll go ahead and draw that. There's my tower. Okay. How long should a guy wire be if it is to be attached 6 feet from the top and is to make an angle of 30 degrees with the ground? So I'm attaching a wire here. It's making an angle. I've got to draw the ground. There's the ground. It's making an angle of 30 degrees with the ground. It says it's attached 6 feet from the top. Okay, if my tower is 220 feet, then, you know, what do I have up there to attach it to? Nothing. So I've got to attach it to the tower 6 feet from the top, which would mean 6 feet below the top. So this piece right here is my 6 feet that I came down to attach the wire to, which means now that this part from here down is how much? Yeah, now that's 214 feet. And what about the tower and the ground? Yeah, we're going to assume those are perpendicular, right? We would think they would be unless we're told differently. We would think a tower would be perpendicular to the ground. Okay, and the question is, how long should the wire be? Give your answer to the nearest tenth of a foot. So the wire is this part right there, right? That's what we're calling the wire. So this would be a right triangle trig here you can use. The key here is to note that we attach that 6 feet down, so that changed the size of the tower piece that we're looking at for our diagram up here. So you might say, what's a trig function you might use here to get side C? Sine of 30 degrees equals the opposite side over the hypotenuse, right? And then are we okay to solve that? Okay. Just the setup is kind of tougher. Let's set up another one here. Okay. Number 10, they've got it set up like this, okay? 10's a little bit, the wording on it's not quite as good, I don't think. But a building 150 feet tall casts a 30-foot long shadow. All right, so there's my building. Okay. It's casting a shadow that's 30 feet long. So down along the ground would be my shadow. It's 30 feet. The building is how tall again? I missed that part. The building is 150 feet tall. Okay. If a person looks down from the top of the building, okay, what's the measure of the angle between the end of the shadow and the vertical side of the building to the nearest degree? They're looking down to the end of the shadow, and they're looking at, that one's worded a little strange. They want you to find that angle right there. That's what they're looking at. Okay, the end of the shadow up to the vertical side of the building. That's what they're talking about, and assume the person's eyes are level with the building. That's what they're looking at. I'll be a little more careful on wording on one like that on the test. Okay. Obviously, I can't put this many problems on the test, by the way. You all would be here for a very long time, wouldn't you? Maybe. So what are we looking for here? What's the measure of the angle? Oh, yeah, this part here. That's what we're looking for. Again, you can use right triangle trig. So just to give you an idea on the setup, and that way you can look back at some of these as you're working through them, okay? What about 11? Let's see if we can set that up. Or here's how I'm going to read it and set it up, okay? So I didn't work through those two, but I've got them set up ready for you to go with them, right? Number 11, two hikers on opposite sides of a canyon. Each stand precisely 525 meters above the canyon floor. All right, so we've got a canyon, right? We have two hikers. I'm so artistic here today. They're on opposite sides of a canyon. Okay, I'm connecting where they're across from each other. They're 525 meters above the canyon floor, so the distance from here down to the bottom of the canyon floor is 525 meters. This is how I'm thinking of it anyway, okay? This is the bottom of the canyon down here. They each cite a landmark on the canyon floor on a line directly between them. Okay, they're each looking at a landmark. So actually right there's going to be where my landmark is on the bottom of the canyon floor. Okay, right here. Because what they're doing is they're looking down at it. They're looking from there. They're looking from there. We cannot assume, though, that it's directly in between them. We can't make that assumption at all. But the angles of depression from each hiker to the landmark meter are 37 degrees and 21 degrees. So where they're looking down from, so that one is looking at a 37-degree angle, this one at a 21-degree angle. And how far apart are the hikers? We're looking for that value right there. How far apart are the hikers? Okay. And again, we're assuming since it was, straight down and we said that the vertical distance was 525, we've got some perpendicular going on there. Again, these are right triangles. What you might want to do is look at each one separately, okay, because you could find this piece right here and then find this piece right here. And then together they would give us what we're actually looking for. Would that be easier to look within both triangles maybe? Just the thought process there. There's other ways I think you can look at this, but this one might make more sense. Okay. So in other words, for the first part, maybe we would say, well, we've got to use that 37-degree angle and that 525 and side A. So what trig function are we looking at there? So the tangent of 37 degrees is equal to the opposite side over the adjacent side. That would give us that piece A up there. And over on the other one also we could use the tangent of 21 degrees would be the opposite side for that triangle over the adjacent side to get side B. So it looks like we've got A times the tangent of 37 degrees equals 525 because we're multiplying both sides by A, right? That gives us A is going to equal 525 divided by the tangent 37 degrees, whatever that stuff is. Over here we're going to have B times the tangent of 21 degrees equals 525. B is going to be 525 divided by the tangent of 21 degrees. So what are these values? Does anybody have those? And then we would have to add them together, though, to get that total distance between the two hikers, because we figured it up, over to wherever that point would be that we go straight down to that landmark they're looking at, okay? That's what we're looking at here. So that's the way I'm seeing the drawing here, and then A plus B, whatever we get there, should equal what we're actually looking for, okay? So you can finish that one, I guess, there. Is this helping a little with the word problems, setting them up at least? Let's go over to 17. I'll look at that one. 17 is a little different looking too. So y'all can finish this one here. And 17. If you have trouble finishing it, send me an email, let me know, okay? All right, number 17. A surveyor standing 53 meters from the base of a building. Wait a minute, I got to draw my building. Oh, that building went underground. Okay, again, right angle. Even though my building looks a little slanty here, the surveyor is standing out here somewhere now, 53 meters from the base of the building. measures the angle to the top of the building and finds it to be 40 degrees. Okay. Looking up to the top of the building. The angle looking up to the top of the building, it says, is 40 degrees. The surveyor then measures the angle to the top of the radio tower on the building. Well, see, they didn't tell us. Now we got a tower up here on the building. There's the tower. And now he's going to measure that angle. Well, my drawing does not look so good. I think I need to take an art class, maybe. That would be useful. Or get some of you who are more artistic to draw for me. I can bring it in too far. All right, well, supposedly it's like a real angle and not slanty up there, okay? So this class is about imagination now in the drawings. The surveyor measures the angle to the top of the radio tower on the building and finds it's 49 degrees. Okay, so now we're looking at this whole piece here. It's 49 degrees. Okay, see where I am there? Including what we already marked, plus that other piece there is 49. The question is, how tall is that radio tower? So we're just wanting this piece right there. How tall is that? How are you going to get that part? Again, maybe you want to work with both triangles. We got two triangles going on here too, don't we? One's overlapping the other. But maybe it would be useful to work with two triangles. I'm seeing, I don't know, what are we seeing? Did it tell me how tall the building was or anything like that? No, it did not, did it? Yeah, we could find out because we can do the tangent of 40 degrees, couldn't we? We'll call this the height of the building right there, okay? It's just from there down. So tangent of 40 degrees will be opposite over adjacent. That would give me the height right there. Then what might I need? Then I could use from the tower down, if I wanted to, maybe call that y. And use the 49 degree angle, couldn't I? So I could use the tangent of 49 degrees is y over 53. How's this stuff going to help me then? Yeah, then whatever I get for y, I can take away whatever I found for h, and that'll tell me how much of that was the tower, right? So y minus h would be the tower. Does that make sense? Looking at that, my drawing's pretty rough on this one, but are you seeing that on this one? Does somebody have a question on what we're looking at? So in other words, first we're just finding the height of the building, then we're finding the height of the building along with the tower, and then we'll subtract the building from the overall. What about those others there? We have maybe enough time to set up one more. 22. All right, 2 points A and B are on opposite sides of a building. I'll just do it like this. A surveyor selects a third point C to place a transit. Point C is 53 feet from point A and 67 feet from point B. See how I'm drawing it there? See how I'm reading through and thinking about what I'm doing? The angle ACB, okay, ACB is this one right here, because they gave all the points on the angle, is 49 degrees. How far apart are A and B? This is what I'm looking for right there. Okay, this is a law of cosines problem. Okay. Well, study, try working through these, see what you can do with it. If you do run into questions while you're working through, you know, either feel free to come during my office time tomorrow, or come, maybe not come, but email me. I'll be glad to answer you by email. I can work the problem out and send you the solution. I'll try to make you some notes on it, okay? Come though Thursday and let's see what we know about this stuff. It's been snowing outside, by the way, so be careful out there, okay? Y'all have a great day. Is it snowing in Kingsport too?
Yes.
Not snowing there? Was it snowing or not, Stephen?
Probably not. I don't see anything.
Don't see any out there? Well, it's snowing pretty good over here. Maybe it's the same one. Okay, and you're looking for solving it. Okay. Yeah, I see there's somewhere that looks like I'm done. Yeah, that's what I. Did you take the square root? I am. Yeah, please, that would be great. Yeah. If you're working that out, you've got a little sheet over here. That's no. Like that.